So, we talked about radioactivity and we hit upon this lambda, right, the decay constant, and another important idea about your half life. So, now it is time to move on to see what are the different modes of decay that are possible. Okay. So, we have radioactivity, we have 4 major modes of decay of interest, right, and as you can see here, some of it is, these are particles, alpha particle decay, beta particle decay. We will go into each of them one by one, but essentially what you see here, there are 4 different ways, of which you could see both particulate, right, similar to how we saw in our X-ray, we had particulate interaction and electromagnetic interaction. Similarly here you have alpha particle, beta particle, and then this is positron decay, and finally you have isomeric transition. So, the last two, in fact this is also a positron is also a particle, but you will quickly see that essentially because of the positron we still are going after. So, it is used in positron emission tomography, right. So, this is used in medical imaging. Isomeric transition, which produces gamma rays, is used also in nuclear medicine, scintigraphy and SPECT. We will see that. So, the other particle interaction. So, we had particle interaction, particulate interaction in X-rays and electromagnetic radiations, right. So, here also there are particulate radiations and electromagnetic HMUs, right. So, like before, these are not of interest to us. What are these? So, alpha decay. What is alpha particle decay? So, essentially we talked about this unstable to becoming stable. The nucleus is unstable, it will try to come to stability, and we talked about this in terms of, remember, neutron and protons, right, how many protons and how many neutrons are there, and we talked about this line of stability. So, if it turns out that it is unstable because of this proton and neutron ratio is not is not close to the line of stability, then what is going to happen? It is going to rearrange itself and send out a alpha particle in this case. What is an alpha particle? Here helium, right, you have H24, this is your alpha particle. So, clearly you can see from here that typically, right, your alpha decay occurs typically in a massive nuclei. So, you see here 106, 263. So, massive nuclei where you have a large proton to neutron ratio. So, what is the objective? So, if it is not along the line of stability, what is going to happen? It is going to shed out, right, it is going to shed out alpha radiation to reduce this ratio of protons to neutrons. So, once that is reduced, it will become little more stable. Okay. So, the idea is this is alpha particle decay, but we will not study more about this because it is not really used for our medical imaging purpose that we are going to talk. So, this happens mostly with we said heavy nuclei. So, atomic number greater than 82, right. So, we will not worry about this. Then you have your beta decay. In beta decay there is something interesting. So, beta decay occurs again when in a nucleus with too many protons or too many neutrons, right, you have this neutrons and protons in the nucleus. When the numbers are not conducive, right, if it is not appropriately distributed, then you have a problem, it is not stable. So, you can have either of this, right, in an unstable form, it may have this imbalance. So, it can switch, right, one of the protons or neutrons is transformed to the other, so that the ratio is brought down to your line of stability, so that it becomes more stable. Okay. So, you can have beta, you can have, when we talked about beta decay, when this rearrangement you can have what is called as beta minus decay. So this beta minus decay is what is simply talked about as beta decay. Here what happens, a neutron changes into proton. So you have neutrons and protons, a neutron changes to proton here, and in the process an electron and a antineutrino are emitted. So this electron is called as your beta particle. So commonly when we say beta decay, they refer to the beta particle that is coming out or the electron that is coming out. Okay. So naturally when the electron comes out with energy, right, it's a particulate, and then that ionizing, that causes ionization. So it's a particulate emission after that, right. So we are not really interested in that. So here you have, notice you have your carbon 614 form and you have your N 714 and that with beta particle and antineutrino. Okay. So what to be noticed, you notice the mass number is same, right, mass number is same, whereas the element atomic number has changed, or in other words your mass number is same, your proton is changed, right. Mass number does not change after decay, proton number increases or decreases. This is what happens in a beta decay. In beta decay, if your electrons come out, right, then it is your typical beta particle emission, beta particle emission, beta D. This we are not going to use. Okay. What we are going to use is another type of beta decay, which is also known as beta plus decay. What is beta plus decay? Here a proton changes to neutron, right. A proton changes to neutron and it gives out a positron. What is a positron? Neutron, proton, electron we saw. What is a positron? Positron is a positively charged particle with a mass of an electron. So you can think about it as a positive charged electron, okay, and a neutrino. So proton, so this rearrangement is the key to make sure that they become along the line of stability. So proton gets converted to neutron, in the process it sends out a positron and a neutrino. Okay. So here also what do you notice? Oh, you notice it's a beta decay. Beta decay can be beta plus or beta minus. Okay, in beta plus or beta minus, the idea is there is a rearrangement of your neutrons and protons. So you notice here in beta plus decay or what is positron decay also, your mass number is same, your atomic number has changed. Okay. So a mass number does not change, a proton number reduces in this case. Clear? So this is your positron decay, but we talked about we are not interested in particles. This is a particle as well, right? Oh, we are not really interested in particulate interaction. We are interested in gamma rays, right? Or that is what we were thinking all along. So what happens to this positron? Are we using it? Yes. You see the modality name, positron emission tomography, you will say, oh, positron is used. But how it is used is, essentially this positron, when it is created, it is not just going to be there, it is going to move, and usually what happens is it hits a electron. There is a free electron that is there. So this positron, after it is created, right, after this beta decay, positron is created, it finds a free electron. When it finds a free electron, it gets annihilated. We talked about this term annihilation before as well. Remember, when the charged particle Bremsstrahlung, right, it can get annihilated by the nucleus. So we have seen this term annihilation before. So here what happens, this positively charged electron, when it moves around, there is a free electron that is there, so they collide and they get annihilated. When it is annihilated, what happens is you generate two photons, that energy gives rise to two photons, which is gamma photons, and then they go in the opposite direction. That is the key. Gamma photons, they go in the opposite direction. What is the energy of these two photons? Oh, you are talking about electrons, right? Either it's positively charged mass or electron. The mass is same, mass is electron mass. So what is the relationship between mass and energy? Half mc square. So essentially this, when this annihilation takes place, the photon that comes out has an energy of 511 kilo electron volt, which is the energy equivalent of the rest mass of electron or positron, because positron mass is same as electron. So right, equivalent of the rest mass. So this is the, so the good news about this is, you know, exactly there is a energy, particular energy that you are looking at, that is one aspect. The other is there are two of them which are exactly going opposite, because the, you know, conservation of momentum. So it will go in the exact opposite direction, 180 degrees apart. See, that is another powerful information, right? So these gamma rays, essentially what we do is, even though it is called positron emission tomography, this positron quickly degenerates, right, and gets annihilated and creates two gamma rays of 511 kilo electron volt. So what do you do is, in medical imaging, this gamma rays that are coming at 511 kilo electron volt, 180 degrees apart, if you can detect, right, which we call coincident detection. We will talk a little more about this when we get to PET instrumentation, but you get the idea. So this is used, even though this is a particle, right, positively charged electron, it is actually the gamma, the energy that comes out because of the annihilation that we are detecting. Okay. So in some sense, once you are able to detect that, you know it is coming along a line, so coincidental. So you can then get an idea on where this decay is happening, where this radioactivity is happening, which is our main idea, right? We are going to send some radioactivity in, based on the measure from outside, we are going to say where that radioactive source is located in the body. That's the big picture, right? Okay, so that is for positron decay. So we have alpha, beta, beta we saw, beta minus, beta plus is called as your positron, and then you have isomeric. Okay, isomeric transition is another way to get gamma decay. So here again the logic is same, you have unstable, but here the mass number or atomic number does not change. It is just so that, look at here, your mass number and atomic number does not change after the decay. What happens is, this is in an excited state, so it has a higher energy state, what we call as meta state. Okay. So a nucleus is unstable, it has a higher energy state, so it has to come to its lower energy state, it will give out the energy, and that energy happens to be in gamma band, so it is called as gamma rays. So here both the parent and daughter are called as isomers, meaning they have, right, you look at here, so it is the same atomic number, same mass number, but you have some energy that is coming out in the gamma range. So we also call this, that high energy state as a meta state, right. So it comes down to ground state and gives, so this is something that is commonly used. Okay, we will talk about this. So where it is used, this is used in your SPECT, right, which is single photon emission. The name is very suggestive, right, single photon, you see single photon that is coming, emission, radioactivity is emitting, single photon emission, computed tomography, we should know by now, we did X-ray computed tomography, that is you catch from outside and then project and say where it came from, right. So you can get an idea. So here, wherever the source is, it is going to decay. If it is going to send gamma rays, on the outside you have detector collect the gamma rays, and then you use your algorithms to reconstruct and say where this single photon is coming from. That is your source of your radioactivity. So source of your radioactivity and how much of radioactivity, those are the key things that we are going to exploit in nuclear medicine. Okay. So the difference, I mean, just to make sure, because we do this comparison all the time, right, because we covered X-ray first and now we are covering gamma rays. Just to alert, we did alert you before as well. So gamma and X-rays, these are all just photons, having gamma having slightly higher energy than your X-rays. So their interaction with tissue will be, right, same physics that we covered before. But what is key here is the origin is different, right? The gamma rays are generation is different. X-ray we talked about energetic electrons, whereas in gamma rays it is generated using isomeric decay or isomeric transition. So the origin is different, but apart from that, the photon, when the photon comes out, how does it interact with the tissue is going to be similar to what we did for X-ray. Even though here we are not interested in, see it's subtle but very important. Here we are not actually interested in the gamma photon interacting with the tissue, whereas in X-rays we were very interested in X-ray interacting with the tissue, photoelectric effect we wanted to maximize, whereas here the objective is not that, right? Hopefully you get that subtle point. We will reiterate this as we go forward. So now the question is, okay, we have this radioactivity and there is a radioactive decay. We talked about half-life, we talked about this radioactivity, and we talked about the modes of decay, how all this radioactive atom decays, right? So now the question is, okay, since we have a formulation, is the decay deterministic? That can I say, okay, if I give this much gram, right? You talked about half-life. So I know the lambda for the material. So can I say that it is deterministic? Not. What you did here, exponential law that we did, right? That gives you what is theoretically expected. However, if you are to do this experiment, take some x grams, x milligrams of a radioactive material, and you observe it over time, some delta t. So it has its half life, right? So you observe over some short time, see how many photons have disintegrated, right? How many atoms have disintegrated, and you take the same material, same everything, same time duration, another time, and do it multiple times. What will you notice? You will notice that you will not get the same expected value every time. This theoretically, this is what you expect using your exponential model, right? Exponential decay law. But you won't get every time the same value. You will be in and around that. But when you average several of them, statistically, the mean will tend to the ground truth or what is expected theoretically. So each time you, even though it's the same material, same lambda, you start observe it over the small time interval, there is a random process, right? The decay is a random process. So the number of disintegrated atoms over a small time delta t. What do we mean by small time? We have some time benchmark, which is your half life. So when you are observing your t over a small time in relation to your half life of that material, of the radioactive atom, right, then it turns out that the radioactivity will follow a Poisson distribution. NO atoms, right, the number of disintegration over short duration, when you start with some N naught of the material at t equal to 0, will follow a Poisson distribution. What is Poisson distribution? We know probability of the disintegrations, right, number of atoms disintegration equal to some k is equal to a power k e power minus a by k factorial. So this a is your mean. What is the mean here in this case? Oh, I do radioactivity, every time I do the experiment I get the number of disintegrations. So mean is lambda n naught delta t, but this is not straightforward, right? This is the value of the mean, this is the Poisson distribution, but this one, let us see if we can agree to this. How did we get a equal to lambda n naught delta t? So we talked about this guy already. Delta t is far less than T half life. So, if that is the case, this distribution is valid and therefore this mean is obtained, right. So, let us think about what happens. Lambda L naught is called as your Poisson rate, that is of interest, right, or Poisson rate, how fast the decay. But really speaking, what do we know? From our previous module, we know, oh, lambda is your decay rate, T half we know as when you have half, right, half life. So, the point is we know in some sense what is the number of atoms that have disintegrated. If you know number of atoms that have disintegrated, so you start with some quantity, some have disintegrated in some time, so you have the remaining. And what did we know about this radioactivity? Radioactivity is proportional to the amount of atoms that are radioactive atoms that are there. That is what we saw, right. So, here in that sense we know your radioactivity is going to be what you started with minus whatever is disintegrated in the time delta t. So, this is strictly your A. This is what you have, radioactivity after delta t. However, you notice we made this assumption delta t is far less than T half. So, if your lambda delta t is much small, right, if this is quantity is very small, then when lambda delta t is small, then you can approximate the exponential to 1 minus lambda a t. In this case, you can get your A to be lambda naught delta t, clear. So, all this is valid for a short time interval of observation. So, you give the radioactivity and the radioactivity starts to disintegrate, right, atom starts to, the radioactive atom is disintegrating. At what rate? Oh, that is characterized by its lambda. All you know is T half is 0.693 by lambda. So, if you are taking observation over a short duration delta t, short in the context of delta t far less than your T half life, then the photons that are the disintegrations are coming, right. So, you are capturing the number of disintegrations, you are counting the disintegrations. That is going to be a Poisson random variable. So, this whole process is a Poisson random process and you have a mean value, okay. So, how do we get a hang of this concept? Just some numbers, let us throw in the context of a typical imaging, right, what is the number that we are talking about. So, you have a patient. So, key information, patient study needs to be completed in no more than 10 minutes, right. This is a practical constraint. I want to do the imaging in 10 minutes, but I need to have at least so many counts of photon, because we will talk about the signal to noise ratio, but you know already number of photons have an influence on image quality. We say X-ray photon, we did that. So, here it is going to be gamma photon. So, you can, the detail might be slightly different how you capture it, but then the concept is going to be similar, right. So, you need maximum more number of photons to have good quality. So, what is that? Oh, at least 3.5 million counts of photons to get the desired image quality. So, now the question is, you cannot do it with more than 10 minutes, you are given that upper bound. You are given a partial information, oh, you are able to count 6,000 photons in the first second, right. So, we are able to count, we are able to detect 6,000 photons in the first second. So, these are the constraints that are given. What is the minimum half life of the radionuclide? So, in order to achieve these constraints, what should be my radionuclides, or at least I could have potential different radionuclides. What is the half life? What is the minimum half life that I should have to satisfy this condition? So what do we do? Well, looking at it, you know, you are given some information here. Within first second I have 6000, right. So this is 6000 photons after radioactivity accumulated over 1 second, right. So you can get your delta n accumulated over 1 second. This is your radioactivity, right. So you have your lambda n naught e power minus lambda t from your previous slide, right. So what is this? This is your 6000, right. This is the number of photons, detected number of photons. So delta n is this guy. Here I am given some n naught times 1 minus e power minus lambda t is given to be 1, right. So this is from first information. What is required? Oh, 10 minutes I want 3.5 million counts, okay, at least 3.5 million counts. So this is going to be again your delta n is again 3.5 million, right, equal to, can it be equal to? No, it says at least 3.5 million counts, right. So we will have to have some, this quantity should be at least means less than equal to n naught into 1 minus e power minus lambda t is 10 minutes, okay. So 1 minute you have 60 seconds, 10 minutes you have 600 seconds, clear. So now what do you need? Oh, you need to find lambda. Oh, I can find, right. If I take the ratio between these two, I can cancel my n naught. So I will be left with only one unknown, right. So if you calculate that, you will get lambda to be 9.45 10 power minus 5 second inverse. Just punch it in the calculator, you should get this, but I hope you understand the logic, okay. So if this is the case, then you can look at what is the minimum half life. This is lambda. From this, what is asked is your half life. Oh, you know the relationship between half life and lambda, right, 0.693 divided by. So if you do that, you are getting approximately about 2 hours. I mean, I hope you get the sense of numbers here. So the idea is the half life is in the order of 2 hours, right, and your lambda, because we made this assumption, lambda t, right, is much smaller than your 2 hours, right. So look at the constraints, you can get still thousands of photons, but they are saying at least millions of photons are required to have a reasonable image quality. So you see the constraint between, if the radioactivity is small, then you will have to acquire for a longer duration, right, because it will take so much more time to give out so many number of photons. If the radioactivity is high, then you will have to quickly catch the data, right, quickly catch the photons, okay. So there is going to be some constraints. So what are the, I mean, we talked about constraints, but the more idea is, okay, so now we understand this idea of sending the radio tracer, and there is this photons that are coming out, modes of decay, we talked about that. And so is there a, and we just had an example where we talked about lambda, right, or half life of the radio tracer. So is there, what are the desired property? So some of the aspects that we covered, we will have to just put it more formally. One is decay mode. What do you think about the decay mode? Oh, the radio tracer should undergo decay, which is good for medical imaging. I don't want particulate, right? I don't want alpha, I don't want beta. What do I want? I want gamma or positron, right? So clean gamma decay. So I don't want these two. So I want to have a radio tracer that can be engineered so that it will have a clean decay, producing only gamma, no alpha or beta. Otherwise you will end up dosing the patient, right? Positron decay will annihilate and again produce gamma ray. So you want only these two. Okay. Energy of the photon. What is your energy of the photon? What is your energy of the photon? We talked about X-ray interacting with the tissue, and there we said if it is too low it will get absorbed. If it is too high it will not interact with the tissue. In our case, what do we need? The photons, should it interact with the tissue or not? Well, it shouldn't, right? We want the photon wherever the radioactivity is inside the body. If it decays and sends the photon, gamma photon out, we should be able to catch the photon and say it came from this location and this is how much it's coming. So we are not really interested if it is going to get attenuated along the path, right? That is not good for us. So the idea is, if you have high energy, we know from X-ray also, high energy it won't interact with the tissue. So you should choose a energy, right, energy of the photon, so that it doesn't interact with the tissue. So it should be high so that the photons can leave the body without or with little attenuation. Because if it is too high, what is going to happen? Oh, you have to detect it, right? So then your detector has to be carefully done. We talked about this earlier. If the body is not detecting, your detector has to detect the energy. So again, your thickness of your detector, all those things what we talked about in X-ray, similar issues will start to come here. So the idea is, you have to have high energy so that it doesn't interact with the body, but if it is too high, it will have difficulty in stopping it on the detector as well. So you have to make sure it is not too high. So roughly this is the range that is operated. Okay. Clearly that means there is some detector material is going to be engineered for this purpose, right? Because in X-ray we didn't really deal with so much of energy. We beam hardened it, and so that was not we didn't really worry about that. Whereas here we have too high is also a problem, and therefore a desired range is this one. Then comes half-life. What do you mean by half-life? Oh, if you think, oh, I need to have a high half-life, meaning radioactivity happens fast. So what will happen? I can have it within a short duration, I can have many photons. So you might be tempted to think that you need a half-life that is high, or in the other words, half-life that is low, right? Lower the half-life, more the disintegrations. So you want, okay, so that logic seems okay, because you want more number of radioactivity to be detected in short time. But what will be the problem if it is too short? If the half-life is too short, oh, you have to give the radio tracer to the body, it has to allow it to go, right? It has to distribute, and then the radioactivity, you have to detect the radioactivity. If it is too short, what will happen is, by the time you prepare the patient and you set it up, your detector may not be able, your detector will not be good. It has to be such fast. So it puts lot of requirements. And the radioactivity, we talked about the T observation should be less, right? Delta T should be less compared to your half-life. You do, right? That is the idea. So if it is already small half-life, you have to acquire even shorter duration. So that becomes a difficulty with respect to logistics. Okay. So you don't want really low. At the same time, you don't want the half-life to be too high. Oh, it's safe, right? Half-life is no problem. This half-life is 1 year, right? No problem, correct. It takes 1 year to get, but then what is going to be the problem? I want to do imaging, I want to see these activities come out, I want to see where it is coming out differentially. So if it is too large a half life, then also is not useful for me from an imaging perspective. So it should not be too short or too long. If it is too long, then like I said, patient scan time will be increased. I have to wait there for a long time before I can catch sufficient photons. The previous example we said, right, some million photons have to be captured. If the half life is so large, then I have to wait there to forever to get the million photons. So there is a sweet spot somewhere in the minutes to hours is kind of desired. So you are engineering these radio tracers, you have radio chemists who do this. So you engineer this radio tracers, these are some of the desired property. Is that all? No, we have some more, right? More importantly, okay, all this is engineered nicely. So with respect to our timelines, half life, all those things are good. That's not sufficient alone. It has to be safe biologically because you are going to give it to the body, right? So this trace quantity should be safe, right? You want to attach that to some compound that you take and it goes. So it has to be safe. That's another important requirement. Okay. So therefore you have some natural candidate for this, say for example iodine, which is naturally available in the body. So you can start to right, in the thyroid, it starts to accumulate in the thyroid. So you can start to have some compounds, you can label some iodines, right, I-123 or I-131 are all sodium salt. So you can label that and administer it orally. So what happens here? Oh, these have a half life that are in the order of days, okay, and therefore this is, since it is safe, right, since this is mimicking your natural iodine, you can allow it, it will take its own time to go, right. You can do thyroid imaging a day later. So you have had enough time so that the body by itself, thyroid will accumulate, right, take all the iodine. So iodine, whatever you gave in the labeled, radio labeled tracer, it will go and you can do thyroid imaging after a day. So you can assess the functionality of the thyroid using this radio. So even though this is in the order of days, right, the half life of this is in the order of days, it is safe and it is kind of labeled using a naturally available compound, and therefore it is safe to use. Likewise, you have technetium 99 which is typically used, right. So it can label DTPA. So what this happens is actually filtered by the kidneys. So that means I can monitor the functioning of the kidney, right. Serial image of kidney can be analyzed to do renal function assessment. So what is the idea of a kidney? Oh, it's doing the filtration. So if I give a technetium based radio tracer, it goes through the filtering, so in the kidney, and so you can essentially start to image that and see how the filtering is happening, right. So this is one another. So the idea is you have to have a radio tracer that can naturally be labeled to find some processes, some functionality, some physiology, okay. That is also an important aspect. You can use gaseous oxygen, only thing is you can not being oxygen 15. So when you do this, what can you do? Oh, it will go wherever blood goes, right. So you could measure the blood flow using this tracer, and of course you can also assess the oxygen metabolism. So the idea is the radio tracers not only should be useful, right, all of these are all safe, okay. Another commonly used safe one is your glucose, right, FDG, fluorodeoxyglucose. Here again the idea is it is very similar to your glucose, it is just that labeled with fluorine. What happens? It will go wherever glucose is going, it gets used, glucose gives you energy, right, so it gets participated in the metabolic activity. So when that happens, the glucose, it does its job. The labeling, right, the fluorine 18, that goes and it goes along with the glucose. Once the glucose is consumed, fluorine stays there. So essentially the more the glucose activity, the more radioactivity from there, because fluorine gets accumulated. So in that sense, this can be used as a functional imaging for metabolic activity. So typically you would have seen some brain scans, right? We want to know, when you think hard, which part of your brain is active. When you are moving your right arm, which part of your brain is active. So brain is using energy, right? So the idea is, even for routine activities, of course, if you have a cancer, like we showed in one of the images earlier for PET, if you have cancer, cancer is aggressive, right? It is going to be metabolically more active. So it is going to use up more glucose, and therefore radioactivity will start to accumulate there and contrast it out. So either or, so these are very routine. So it's going after the functional aspect. Okay. So not only should it be useful, it should be safe, and it should be able to participate in the functional aspect without affecting the function. So it cannot change the function. So it has to participate there. So here, for example, fluorine does not participate in anything, glucose does its job. Fluorine goes there and sends, oh, here is where the glucose is getting used up. It will send that information, right? Or at least you can infer that it does not alter the metabolic activity per se. Okay. So those are the desired properties that you would want for your radio tracers. Of course, last but not the least, we would like it to be monoenergetic. We had this wishful thinking even for our X-ray, right? Why? Because see, if it is monoenergetic, if I know I am going to get only one energy, then any other energy I know is coming from some scattered gamma, right? You have your Compton scattering. So the gamma photon could get scattered, similar to your X-ray, right? I mean, so Compton scattering can happen. So if you have a range of energy that is coming out, then you do not know, some is from the signal, some is from the Compton. Whereas if you get only one energy, then you know anything apart from this energy is probably from Compton scattering. So energy sensitive detectors can discriminate primary photons from scattered ones. So if you have monoenergetic, right, the radioactivity, the tracer that you have, if the radioactive decay happens such that it gives one energy only, right, then that is preferred. So for this reason, example is a technetium, right? Technetium is a, we did see that earlier as well. So here this can be prepared on site, okay. And like I said, this metastate, right, is usually intermediate state. So you have this molybdenum that gets, when you do this preparation, it gets to your technetium 99, which is in the higher energy state, which we call as the metastate. But it cannot stay in that metastate for, right, because it is a high energy unstable state. So immediately what it will do is, it will give out gamma rays and come down to more stable technetium 99. So the idea is, you can prepare this, right, at the site before administering. And so the characteristics, if you see for this, half life is about 6 hours, energy is 140 kilo electron volt. So now you see the thing, oh, half life in the order of hours. So it is neither too short nor too long, and also you get only one energy. Okay, so this is very desirable. So we are talking about desirable conditions, right? So you have gamma decay, okay, modes of decay, gamma decay, good. Then monoenergetic, good. Oh, half life, neither too long nor too short, good. Safe, it can be labeled with several things, right? So it can be tagged with variety of molecules like sulfur, colloids, albumin, phosphates. So you see already that because of all the, it ticks, right, checks out most of the desirable properties, and therefore more than 90% of nuclear imaging studies use technetium. Okay, so this is we talked about some of the desired property, and this is a routinely used one because it satisfies several of this. By the way, there are maybe 1000, 1200, 1500 radio tracers that have been developed. Maybe about 10, 20 are also available in the market, right, as a compound that can be used. Each one has, if depending on the functionality that you are imaging, some have some requirement, so you have those, but 90% of them you have technetium, right. So you look at where you started out, you have say 1000, 1500, but then when you start to put all the desirable features, you come to a handful, okay, and then maybe you have to still custom make it for certain disease, certain physiology that they want to understand. Maybe you will have to create a new compound. So this is what the active areas that people pursue in radiochemist, for example. How do you prepare? How do you synthesize this? How do you, there is process, there is several levels of understanding there. And finally, of course, how do you use this for a particular, can you label it? Does it really uptake in the body? Then is it safe to take that? All this is a very involved skill sets. Of course, from biomedical engineering perspective, our interest is, okay, we understand all this. So when I say I want better image quality, I know the complexity involved in the signal origin. These are all signal origin, right? I give the radioactivity, after that I get the signal. So this is signal source. So there is a lot of engineering for that. But typically when you are looking at a imaging systems perspective, you are an imaging engineer, you have to understand, appreciate this problem, and therefore we can, we'll have to do the best we can with respect to the other components that are in our, at least we think that we have some more control. Say for example, your detector, your setup, right. Okay. So to summarize, radioactive decay is a process where you have your unstable nuclide changed to more stable one. In that we talked about the different modes of decay. You have particulate decay and also you have gamma. Only the gamma is used in, gamma rays is used in your medical imaging. So we also talked about this radioactivity, right. You can model that using an exponential decay law. And when we talked about that law, we talked about the half-life as well. So you have an exponential model and then you have a half-life that is usually characteristic. And we went on to talk about some of the desired property of radio tracers and also few of the radio tracers that are commonly used or routinely used. So this is a good time to stop the physics of radioactivity. Then we will, in the nuclear medicine, remember, we will now move on to the different modalities that exploit the gamma rays. Okay, your SPECT, right. So if you really think about it, SPECT is having a tomography. When we did X-ray, physics, we started with projection radiography, right, chest X-ray, right, projection radiography. So like that we have an equivalent here, analogous here, which is scintigraphy. So we will start with scintigraphy and then we will go to the tomography. So SPECT will be single photon emission tomography and then we will have positron emission tomography. Okay. So with this physics we should be able to cover the instrumentation and the imaging equations and image quality for the three modalities: scintigraphy, planar scintigraphy, SPECT and PET. Okay, thank you.